Welcome everybody to another short video on force and momentum this time. So why is momentum important? Why is mass times velocity important? Well, it's all to do with forces. As you can see here, force is equal to mass times acceleration, which you should know from previous study in Newton's laws. But this can be then converted and written into another formula in terms of momentum. As acceleration is equal to the change in velocity divided by the change in time, we can convert that out into our force equals mass times acceleration formula to create a force equal to change in momentum. You have to remember that a change in momentum is always resulting from a force. We could consider an object, and it is moving with some velocity towards a wall. Now, when it hits that wall, it'll rebound with another velocity, but to do so, it required a force. And what that force is the question. And so we use the formula I'm about to show you to calculate the force in this kind of situation. So, we've got force is equal to mass times acceleration. We've just had a look at how acceleration is the change in velocity divided by the change in time, and so we're going to convert that out into our velocity, take velocity initial over change in time. We can now use this instead of acceleration. And by doing that all the way over here, we are able to get force is equal to mass times velocity, take velocity initial, over change in time. Now you may be able to notice something here. It's pretty straightforward. We can convert our top line here into momentum. And so doing so gives us force is equal to mass times velocity, take mass times velocity initial, all over change in time. So in this situation now, what we're able to do is convert our mass and velocities out into momentum. So effectively what we have is momentum, take momentum initial over change in time is equal to force. And if you want to go even further, that effectively can be changed into, using our known delta sign, force is equal to change in momentum divided by change in time. And so this is our kind of underlying momentum to force formula that we will be using. And all this is, of course, just from Newton's second law, which is pretty fantastic. So where do we go from here? Well, basically what we're trying to look at is another way to understand force. And a good way of describing this is a force on a moving object can be defined as the rate of change in momentum of that object. So that force is described as how much the momentum changes, and vice versa. You can see our formula here that we calculated out just before. Very dodgy arrow though. Anyway, so you should be understood that change in momentum is signified as delta P and change in time is delta T, and those are in newtons and seconds respectively. So then, let's have a look at a question. A bouncy ball of a mass 100 grams bounces vertically on a cement floor. Its velocity changes from 10 meters a second minus 1 to 5 meters a second to -1 up in 0.1 seconds. So that would be 10 meters a second when it's traveling down, and then it's moving upwards with 5 meters a second minus 1. Okay, that makes sense on our concrete floor. Time taken was 0.1 seconds, and our mass was 0.1 kilograms. So I've immediately converted that one out from the 100 grams there in the question. Okay, let's go to a math board, and we'll move that out the way. We'll use our 4F method like normal, starting with the facts. So we have a mass equal to 0.1 kilograms. We had an initial velocity equal to 10 meters a second. I'm going to leave the downwards direction as the positive, so that's why it's just 10 meters a second, whereas the velocity final was equal to negative 5 meters a second minus 1. Remembering that you do have to define the direction, either in a worded manner or by using a minus sign there to signify direction. So we want to try and find the force. What is the force that affected that ball? Okay, I like to draw a diagram if I can get away with it. So let's do a quick ground example here. Just like before. Ball moving down 10 meters a second minus 1. And then you can imagine the after effect. Ball moving upwards 5 meters a second minus 1. Well, we've used our formula now of force being equal to change in momentum over change in time. And if we go now to our expanded formula, we would end up with force is equal to mass, velocity, take mass, velocity 1 over delta P. Delta T, time. So we've got our final and initial velocities there. So we're going to move now to our find it section. And so our force is now equal to 0.1 multiplied by 10. Oops, instant error there. That's our initial velocity, multiplied by minus 5. Take our 0.1 mass times by 10, which is equal to, don't forget the time. How long did that take? 0.1 seconds, looking back at the question. Okay, multiplying these through, we've now got negative 0.5 take, 10 times 0.1 is 1, take 1. That would be equal to negative 1.5 over 0.1. Let that be divided, and we've got force, and this is our fix it section, so I should probably do it in a separate colour. We had very much yellow. Force is equal to, in this case, negative 15 newtons. And that could be rewritten as the wall, or the floor I should say, imparted 15 newtons of force up, which in brackets is against the direction of the ball. And there you go, that's how we can use that formula to calculate out the force involved in an object when we can calculate out its momentum from its change in velocity when we have a known mass. And that's a good example. All right, see you in the next video.